Okay guys, so today we're going to go ahead and get started with Unit 1. We are going to talk about our rational and irrational number properties. So just to refresh us, a rational number is a number that can be written as a fraction or a ratio. Beautiful part of that is the hint of the word, the context clue is right there. Ratio means fraction. So we can write this number as a fraction. So that can be an integer, because that means we put it over the denominator 1, a fraction, a decimal that ends, or a decimal that has a repeating pattern. So some examples, that integer could be 12 or -7. The fraction could be 4/5. A decimal that ends, so we could have maybe 7.25, -3.8, or a decimal that has a repeating pattern, so maybe 1.2323 ... So that ... tells us it goes on forever, but because we have 2323, we know there's a repeating pattern there. Okay, so that is our rational number. Okay. The next type of number we have is an irrational number, and that's just a number that cannot be expressed as a fraction. Common examples of irrational numbers are non-perfect squares and decimals that go on forever with no repeating pattern. So these, a non-perfect square is something like the square root of 85. Okay, so we know that the square root of 81 equals 9. So that simplifies to a whole number, so that's why it's a rational number. But a non-perfect square is going to be irrational. Another common one, square root of 2. Pi is also an irrational number because it's 3.14159 ... and it goes on forever. Okay, and then we could also just have a random decimals, maybe 7.356214738. Okay, and it goes on forever. We don't know what the pattern is, so we have to say it's irrational. Okay, and then we have this next definition of closure. And closure is just talking about this idea that if we apply an operation to something, our answer will stay in that set. Okay, so we can have this set of rational numbers, irrational numbers, integers. I like to go ahead and just start with an easy one. Think about even numbers. Okay, so if we add an even number and another even number, our answer is an even number. Okay, so even numbers are closed under addition. Okay, so in an example with actual numbers, 8 plus 8 is going to give us 16. So we took an even number and added another even number, and our answer, or the sum, is also an even number. Okay, odd numbers are not closed under addition. Okay, because if we did 7 plus 5, we get 12. So we did an odd number plus an odd number, but got an even number. So our answer is not an odd number, so it's not closed. Okay, that's probably the newest term for us, and we're going to practice a little bit more with it. So the next part we have, we're looking at these rational and irrational numbers. So is the product of two rational numbers always going to be a rational number? So if we take two rational numbers and add them together, will our answer always be another rational number? Go ahead and hit pause and think about the answer, and then we'll come back and check. Okay, so the answer is yes, because no matter what we add, we're either going to be adding an integer to an integer. So 12 plus 5, we're going to get a rational number. Square root of 25 plus square root of 100, that gives us 15. So yes. 7.25 plus 8.4 is going to give us 15.65. So yes. 4/5 plus 5 yeah, 5, whatever, sevenths. We get a fraction, so yes, it will also be a rational number. So rational numbers are closed under addition. And I apologize, guys, I switched these. So I don't know why I have multiplication first, guys. I'm sorry. So yes, they're closed under addition. Go ahead and hit pause and think about if it's closed under multiplication. Okay, so again, guys, yes, rational numbers are closed under multiplication, because if we multiply the two, we will always get a rational number. So square root of 4 times the square root of 25, we're going to get square root of 100, which equals 10. 12 times 5, we get 60. If we multiply a decimal times a decimal, we'll get a terminating number. If we did a fraction times a fraction, we get a fraction. So yes, they are closed under, rational numbers are closed under multiplication. We can do the same thought, but now with irrational numbers. Okay, I'm gonna go ahead and do the addition one because I think that's easier to start with. So think our irrational number is going to be closed under addition. Go ahead and hit pause and see what you think. Okay, so irrational numbers, let's go ahead and think of some examples. So maybe square root of 2 plus the square root of 7. No, that gives us an irrational number, so yeah, that's good. Pi plus the square root of 2 gives us an irrational number. So, and I mean, if we did a 7.3458 plus 7.3458, it's going to go on forever, so yes, that's going to be irrational. But what about the square root of 2 plus the negative square root of 2? That's going to give us 0, and that is not an irrational number. Okay, so irrational numbers are not closed under addition. Okay. And then we can also follow that same thinking with the multiplying to get the product. So if we multiply 2, so square root of 2 times the square root of 7, that's going to give us the square root of 14. That's irrational, so that checks out. Pi times the square root of 2, that's going to give us square root of 2 pi, which would be irrational. And then if we multiplied 7.358 times 7.3458, we're going to get an irrational number, okay? But if we follow the same logic, what if we did square root of 2 times the square root of 2? So we did an irrational number times an irrational number. We're going to get the square root of 4, which equals 2. This is a rational number, okay? So again, not closed. So, in summary, rational, closed under addition and multiplication. Irrational, not closed under addition and multiplication. Okay, so basically with rational numbers, we're always going to get a rational number. But with irrational, our answer isn't always irrational. Okay, so basically that's what it's saying with closed under addition multiplication. For rational numbers, we always get a rational number as our answer. If it's not closed, we don't always get an irrational number. Something for us to think about, are rational numbers closed under subtraction and division? Yes, they are. So subtraction, we can say yes because we're doing opposite addition. Okay. And then division, you're making a fraction. So yes, okay? Because when we make this fraction, we're gonna say maybe 5 divided by 8. You just made a rational number. So it will be closed under division. So I have some few examples for us to look at really quickly just to practice. So determine if each number is rational or irrational. For time's sake, I'm going to do an R for rational and an I for irrational. Go ahead and hit pause, go see what you guys can answer these as, and then hit play to check your work. Okay, 7.111, since the 1 is repeating, it is rational. 2, we have negative 3.0202202220, and it goes on forever. There is a pattern, but it is not a repeating pattern, so it would be irrational. Square root of 25 is a perfect square, so rational. Square root of 27 is not a perfect square, so that would be irrational. 4.534, and then the line over it tells us we're doing 534, 534, and the pattern goes on, so rational. 4 over 11 is a fraction, so rational. Square root of 121 over square root of 100 is equal to 11 over 10, because both of those are perfect squares, so rational. And then square root of 25 over square root of 10 is going to equal 5 over the square root of 10. Since we cannot simplify this denominator, we're going to say it is irrational. Okay? So explain whether irrational numbers are closed under addition. This was basically from the notes. So irrational numbers are not closed under addition, and then our example to say why is because the negative square root of 2 plus the square root of 2 equals 0. So we took an irrational number plus another irrational number and got a rational number, makes it not closed. Okay, rational numbers are closed under multiplication. And our reason or our example we had is because you always get a rational number as your product. Okay, and we can say 5 times 4 as an example. And then with this last part, evaluate each expression. So if m equals 2, n equals the square root of 5, and p equals 1/9, we can substitute these in. I'm only going to do one of these as an example. So number 11, n squared minus m. So n squared, the square root of 5 squared minus n, which is 2. Square root of 5 squared is going to be 5 minus 2. We get 3. That is a rational number. I'll go ahead and do number 12 too. I lied, I'm going to do 2 of them. Square root of m times n, so square root of m, so square root of 2 times the square root of 5. We get the square root of 10, and that's going to be irrational because that's not a perfect square. Okay, if you would like to try the remaining ones, you may. If not, you can go ahead and be done. Thanks, guys.